Hello students, welcome back to the 7th video of this playlist. In this video, we will be solving question number 16 from the most recent past paper of Physics Unit 4, which is the October 2024 Physics Unit 4 paper. So let's get started with question number 16 from this paper. Okay, here you go. So here in question 16 it says the diagram shows some equipment used by a teacher to demonstrate the action of electric fields. Okay, a long white plastic track has strips of conducting material attached to it. The strips on one side of the track are connected to a potential of 1800 volt. The strips on the other side are connected to a potential of 0 volt. So the PD is given. A ball with a conducting surface can be accelerated along the track. We can see in the figure it looks like pretty much like a linear accelerator, isn't it? Okay, so here part A is asking here the teacher places, it says the teacher places the ball on the first strip. Okay, we can see the ball has been placed on the first strip. The teacher switches on the power supply and the ball accelerates. The size of the gap between the strips is 2 centimeter. Okay, the size of the gap between the strips is given as 2 centimeter. So part A1, it's saying the ball accelerates uniformly across the gap between the first strip and the second strip in 0.22 seconds. The time is given. The distance between the strip is given. Now they are asking to show that the acceleration of the ball is about 0.8 meter per second squared. So here initial speed is 0 meter per second. It is starting from rest. Time taken, it is 0.22 second, right? And then the distance is given as 0.02 meter. So we need to find out the acceleration. So we can use which formula? S equals to ut plus half a t squared. Okay, so ut is 0, so twice of s equals to a t squared. So we need to find out the acceleration. So a equals to twice of s over t squared. So twice of the distance, this is 0.02 over t squared. Time is here 0.22 squared. So what we will get the acceleration, 2 times 0.02 divide 0.22 squared. So that will give you okay, so we will get 0.826446 meter per second squared. So we can write it to 1 decimal place as 0.8 meter per second squared. Showed. So the required acceleration is 0.8 meter per second squared. Fine. Okay, next is part 2 of A. Okay, so here the question says when placed on the first strip, the ball is charged to a potential of 1800 volt. Show that, the question is asking to show that the charge on the ball is about 2 times 10 inverse 9 coulomb. So radius of the ball is given as 0.95 centimeter. Okay, so consider this is the ball. This is the ball. Okay, and this is the center. So center to surface radius, it's center to surface length, it is the basically the radius 0.95 centimeter. Okay, so it is charged to a potential of 1800 volt. That means when it is connected to the power supply, it was supplying 1800 volt on the surface of the ball. Okay, so the potential is 1800 volt. So we know that electric potential, the formula for electric potential, it is what? V equals to KQ over R. Okay, so we need the charge. So Q equals to V times R over K. So V is 1800 times the radius. the radius it is 0.95 over 100 over the value for k, it is 8.99 times 10 to the power 9, that much coulomb. So let's figure out the value. So 1800 times 0.95 over 100 divide 8.99 times 10 to the power 9. So that will give you 1.902 1.902113459 times 10 inverse 9 coulomb. Okay, so which can be written as 2 times to one significant figure, that is 2 times 10 inverse 9 coulomb. That's it. Fine. Okay, next is part 3. In part 3, the question says there is a force on the ball due to the uniform electric field between the strips. Okay, deduce whether this is the only force acting to accelerate the ball at about 0.8 meter per second squared. Mass of ball is given, it is 0.18 gram. Okay, so to figure out that whether the force from the electric field it is the only force acting on the ball or not, we need to find out the acceleration that the electric field will provide to the ball. Okay, so to find out the acceleration we need at first the force. Okay, so for force in electric field we will consider the equation, since it is uniform electric field and we know the PD is 1800 volt there. So we know that electric field strength in uniform field it is E equals to V over D. Again, E equals to force per charge per unit charge, so we can write it as F over F over Q. Fine. So what we will do at first is that we know the distance between the strips are known, which is 2 centimeter. If I'm not wrong, it was given earlier, it was 2 centimeter exactly, 0.02 meter. Okay, so 2 centimeter. Okay, so we need the force here, so F over Q it is equals to V. V is 1800 over the distance, it is 2 centimeter, so 2 over 100. So F over Q it will give you 1800 over 2 over 100. So this is basically 90,000 Newton per coulomb, F over Q. So we need now the force. So F equals to 90,000 times the charge of the ball. The charge of the ball it is exactly 1.901 ... times 10 inverse 9, that much Newton. So the force we will get here, force can be written as MA. Okay, so 90,000 times the exact value for the charge, it is 1.902113459 times 10 inverse 9. Okay, so we got the force, which is 1.711902.113 times 10 inverse 4 Newton. So we will divide that by the mass. So 1.71 ... times 10 inverse 4 divide the mass is 18 grams. 18 gram. Okay, not 18, it is 0.18 grams. So 0.18 times 10 inverse 3. So you will get 0.18 divide 1000. Okay, so 1.71 times 10 inverse 4 divide 0.18 over 1000, that gives you 0.951056 7 295 meter per second square, which is greater than 0.8 meter per second square. So the deduction is that the acceleration from the electric field, it is basically it was supposed to be larger, but the actual acceleration is it's what, smaller. That means hence the force from the electric field is not the only force acting on the ball. Hence the force from the electric field is not the only force acting on the ball. That's the deduction. Fine. Okay, next is part B. Part B of question number 16. Okay, here in part B, the question says the equipment can be used as a model to demonstrate the acceleration of charged particles in a Linac. Just at the beginning of the question, I said we can it's pretty much like the model is pretty much like Linac, right? So here they are comparing the model with Linac. Okay, when placed on the first strip, the ball is charged to a potential of 1800 volt. The ball then accelerates towards the next strip at 0 volt where it discharges. Okay, so initially when it is on the first strip, it gets charged, and after getting charged, it accelerates from this between this region and then reaches the strip at 0 volt. Here the ball gets discharged. At this strip, the charge get discharged. Okay. The ball then moves at constant speed to the next 1800 volt strip. So that means from X to Y, it moves with constant speed. Okay. The ball is charged again. Okay, the ball is charged again and accelerates to the next 0 volt strip. Okay, so again after moving with constant speed between X, Y, it reaches 1800 volt, that strip, and at that strip it will get charged again. Okay, this pattern of movement continues until the ball reaches the end of the track. The diagram shows part of the model. Okay, we can see this is the part of the model, and there is a shaded region XY. Okay, so part 1 here, it says the shaded section of the diagram between X and Y corresponds to the drift tube in a Linac. Okay, drift tube. A drift tube is basically like this in a Linac. So they are comparing this shaded region with a drift tube. Okay, give one similarity and two differences in the way this section of the model works. This section, not the whole model, only this section of the model works, and the way a drift tube in a Linac works. Okay, we need to say one similarity. Okay, at first the similarity. What's the similarity we can say here in this case? So here we know that at first consider for Linac. For Linac, we know that within a drift tube, XY is basically a part within. This is a section of drift tube. They are considering this section, comparing this section with the Linac. Okay, so within a drift tube, we know that the particle moves with constant speed, right? And here also the ball is moving with constant speed. There is no resultant force acting on the what, on the ball, right? So the similarity is that within a drift tube of Linac, a particle moves with constant speed constant speed, and here in the model the ball is moving with constant speed between x and y. X and y. This is the similarity. Now the differences. Okay, consider the differences. So now difference, similarity, and now differences. For the differences, what we can say, look, here, okay, for Linac, at first consider for the Linac drift tube. This is the drift tube of a Linac. So for a Linac drift tube, within the drift tube there is no electric field, right? But here in this model, between x and y, there is an electric field from 0 volt to 1800 volt. Now you might ask, then how the ball is moving with constant speed between x and y? Because the ball is discharged. It is discharged at 0 volt. It is discharged here. Since it is discharged, so it has no charge within it. So therefore, it will not affected by the ball. The discharged ball will not get affected by the electric field. So that's why this is the difference. In within a drift tube there is no electric field, but here in this model there is what? There is electric field between x and y. Within the difference is within a drift tube there is no electric field, but the section of the model has an electric field between x and y. We have said the section, so this means x and y. Model has an electric field. This is the one difference. The last difference what we can say here is that okay, this is, we are comparing it with the drift tube. Okay, so in Linac the length of the drift tubes increases, right? Okay, the length of the drift tube increases, but here the length, not the length, we can say the distance between the strips, it is constant, 0.02 meter. Okay, so in Linac the length of drift tube increases, of the successive drift tubes, successive drift tube increases, but here in the model, the distance between the strips is constant. Okay, so these are the two differences you can say, and this is the one similarity we can say. And another, instead of the last one, okay, for different, in case of differences you can say another difference here, which is that the charge within a drift tube, the particle is basically charged. The particle is charged, particle moves through the drift tube, right? But here in this model the ball is discharged. It is discharged at the 0 volt, so it is uncharged, ball uncharged. So an uncharged body is moving through the section xy. So that's another difference you can say. Okay, so That's the answer for part 1 of B. Fine. Okay, next is part 2 of B. Okay, here the question says in the model the lengths corresponding to drift tubes are constant. So the question is asking to explain why the lengths of the drift tubes in a Linac are not constant. Why the lengths of the drift tubes are not constant. Okay, so in Linac we know that within a drift tube the particle is moving with constant speed, but as it moves from one drift tube to another drift tube, between the drift tube it accelerates due to the presence of electric field, right? So since it accelerates, its speed increases. Therefore in the next successive drift tubes it will travel with higher speed, with faster speed, and therefore the length of the drift tube should get increased, because the supplied PD to the drift tubes it has a constant frequency, that is it has a constant time period. So that's why the accelerated particle the accelerated particle should elapse same amount of time in between each drift tubes. Okay, so what we can say here is that the first point, the particle accelerates between the drift tubes so speed increases the power supply has constant alternating the power supply gives alternating current of constant frequency so time period is constant. Okay, so the third point for 3 marks, the third point is that so the particle should travel, so the particle should elapse equal time between the tubes, and hence as speed increases the length of tube should be increased to keep the time the elapsed time constant. Give reference to the equation S equals to Vt. As V increases, distance should be increased. As V increases, distance should be increased, because T should be constant. That's why. That's it. That's the answer for part B 2 from question number 16. Fine.